All right, guys, so let's continue talking about coupled equilibria. I just have one more example for you here. And remember, you want to review chapter, I think it's 13, review the coupled equilibria. So this is stuff that we already learned about. We're just kind of applying it to a new situation. All right, so review the coupled equilibria. I'm just going to do a quick review here so you can see some examples of what I'm talking about. So for example, if we have A going to B in an equilibrium, and let's just say that this K's value is 10, right? Then we can have a situation where we're going from B to A, and let's say this K value is question mark, right? We want to figure it out. We want to use this top one, number 1 here, to figure out number 2 here. And so going from here to here, what you can see is that we've essentially flipped the reactions, right? In the top, A is a reactant, B is a product, and vice versa in the other, right? So we flip the equation. And so if we take a look at what the K values here would be, it's always K is always products over reactants. So here would be B over A, right? Whereas down here, we would have A over B, right? So you can see when you flip this equation, we take the inverse, right? So that's the same thing as raising it to the -1 or, taking the inverse. So X goes to kind of 1 over X. You're flipping it. So anytime you flip the chemical equation, you take the inverse of K. So if you know that this K's value right here is 10, then what we can do here is we can flip this K. We'll call this K1, we'll call this K2. So we can say K2 is equal to K1 to the -1, which is equal to 10 to the -1, which is equal to 0.1. So again, that's what these coupled equilibria are all about. Taking something that you know and figuring out something that you don't know. So there's an example of flipping the equation. That's not the only thing we can do, though. Sometimes we can multiply equations. So in this case, if you have A going to B, what would the K of 2A going to 2 be? Assuming this K, again, we're going to go with 10. Here, K2, question mark, right? How do we figure this out? So you can see here, when we go from the top equation to the bottom equation, we double. Right? And if we were to write out the K's here, this would be K B over A, right? Products over reactants. This K here, oops, get rid of this K. This K here would be B squared because of these coefficients over A squared because of the coefficient. So you can see when we go from here to here, we're going to want to raise it to that power. So if we double, you need to raise it to the second power, right? So it's going to go from X to X squared. If you're tripling it, you'd cube it. If you were halving it, you'd take it to the 1/2. If you were thirding it, 1/3, so on and so forth, right? So we can say here that K2 is equal to K1 squared, which is equal to 10 squared, which is equal to 100. Again, taking something that you know and transforming it into something that you don't know to figure it out. So you can flip equations, you can multiply equations, and then one last thing. So let's take an example of A in equilibrium with B, and then B in equilibrium with C. And let's say we know these K's. This K can be 10, this K, let's just say 5, just some random numbers I'm making up. And then we have something like A going to C, and this K is equal to question mark, right? So let's try to figure this out. Well, if you take a look at these two top equations in relation to this bottom equation, what you can see here is that if you sum them, right, if you try to sum them, what's going to happen is things that show up on both sides are going to cancel out. So when you sum these, this B and this B will cancel out, and you'll get A in equilibrium with C. So you can see when you sum the equations, you get what you want. So go here, sum. So let's see what happens to the K's when we do that. If we think about the K here, again, products over reactants, it'd be B over A. If we think about the K here, C over B. And if we think about the K here, what we want at the end is C over A. So in order to get these two to look like that, what you have to do is you have to multiply them. So let's take a look at that. So we'll call this K1, K2, and K3. So if we take K1, multiply it by K2, what we have is B over A times C over B. And mathematically, you should be able to spot very easily that these two B's will cancel out, right? They're divided by one another. And then you get C over A, which is exactly what you wanted it to be. So this is equal to K3. So then we just plug in the numbers, right? If all of this stuff is equal to K3, we pull the numbers right here. We said K1 was equal to 10. We said K2 was equal to 5, right? I could pull this from up here. 10 times 5 is equal to 50. So the value of K3 here of our overall reaction is 50. So again, just to recap, if you flip an equation, you take the inverse of the K. If you change the coefficient of the equations, you'd raise it to that power. This thing right here is supposed to be a caret, so raise to that power. And then if you sum equations, you multiply their Ks. So equilibria are super important in terms of biological functions and ecological, right, environmental functions. So let's just take a look at a cool example from the book. So we'll just call this another example, and we'll see how we're using this K stuff to actually apply it to something to figure something out. So let's just say you're chilling in your car, you're driving your car. This is a car, right? That's you driving the car. So you're driving this car, right? And let's say you went to a little vacation and you saw the coral reefs, right? So they're really nice, pretty colors. I don't know if they're these colors, but they're cool colors. So we'll call these guys right here the coral reefs. So if you kind of pay attention to the news, one thing that you'll know is the coral reefs are dying. So let's take a look at example what the coral reefs are. The coral reefs are made out of calcium carbonate as a solid, right? Calcium carbonate is generally considered insoluble, so it's existing as a solid. If it weren't a solid, the coral reef wouldn't be there. And so this can dissociate into calcium 2+ and a carbonate. But what we see that this KSP value is 8.7 times 10 to the negative 9, right? So this is really small. And so small k favors the reactants. In this case, the solid calcium carbonate. So that's how these coral reefs can exist. So let's take a look at what's happening to the coral reefs and why. So when you're driving to leave the coral reefs, your car's pumping out some fumes, and inside these fumes are carbon dioxide. Carbon dioxide can dissolve and react with water. When carbon dioxide reacts with water, it forms carbonic acid, right? CO2 plus H2O equals H2CO3. Take a look in the previous notes. We saw the mechanism of this reaction when we learned about Lewis acids and bases. So it forms carbonic acids. So let's figure out what carbonic acid does to the coral reefs. So carbonic acid itself, as the name implies, is an acid. So it's in equilibrium with H+ and bicarbonate. This Ka1 here is equal to 4.3 times 10 to the negative 7. So it's a weak acid. But it's also diprotic acid. You see, we still have an H left over. So it can actually donate another proton. Oops, this should be negatively charged. H right here, H plus CO3, 2-, right? And so this Ka2 is equal to 4.7 times 10 to the negative 11. right? When it donates that second proton. But what we can see is we have a common ion here. Here we have carbonate, and here we have carbonate. So let's take a look at what happens when you flip this reaction. So when we flip this reaction, this becomes CO3, 2 minus, plus H plus, to HCO3 minus. And of course, we would flip the Ka. So this K, call this K2, is equal to 1 over Ka2, or Ka2 to the -1. Cool. So we flip that reaction. Now let's see what happens when we take these two reactions and we add them. So I'm just going to rewrite this reaction right here. So calcium carbonate in equilibrium with calcium 2 plus and carbonate 2 minus. And then I'm going to sum these last two equations, right? Just these last two. And so what I notice is that carbonate is on both sides. So both of these go ahead and just cancel out. And then the end result is calcium carbonate plus H plus, an acid, right? This is solid. This is bicarbonate plus calcium 2 plus, and this is aqueous. We summed these two reactions. So we'll call this K3, I guess, and it's going to be equal to this KSP right here times this Ka2 to the inverse. And so when you plug and chug through these, you get 180. And so this number, this K is not huge, but the products are slightly favored. Right, and if we take a look at what our products are, that means that this right side is slightly favored. What it means is that this bicarbonate is favored, and this is an aqueous solution. So if your coral reef is over here it would be no coral reef, because the coral reef is literally dissolving away. And so what does that mean in terms of the environment? Well, it means that the coral reefs essentially die. So if you take a look at this picture right here, on the left, we have a nice blooming coral reef on which organisms can live. And then on the right, we have kind of no coral reef, essentially. The coral reef is dissolving away rapidly, and so all the organisms cannot sustain their life here. And so the coral reef dies, right? And you get sad because the coral reef's going to die. And so you can see how this equilibria, all the equilibria in the world are coupled. And so something that you do on one side of the planet, it affects the other. So all the CO2 that we're pumping out is having an effect on the coral reefs due to the value of these Ks and these interaction, the way these equilibria are coupled. And so that's true in a lot of different instances. There's another very cool example in your book, in the OpenStax book. It's page 843 to 844, and it basically explains how tooth decay works. So this case stuff that you're learning, it's very applicable, very cool, very important. In the upcoming chapter, thermodynamics, we're going to see why K is what it is. Why is this KSP 4.3 times -7? Or my bad, why is this K 8.7 times 10 to the -9? Why are these values what they are? That's what we're going to learn next in thermodynamics. So again, review your chapter 13. Chapter 13, coupled equilibria, be able to do these types of problems, be able to flip equilibria, be able to multiply equilibria, be able to add equilibria. Good luck.